Good morning everyone. I hope you are all doing well. My name is Dr. Amar Kumar De and I am excited to welcome you to today's lecture titled AM and FM receiver for the course Fundamental of Communication System and its Application. It's exciting to see so many of you joining us from different corners of the world. First and foremost, I want to extend a warm thanks for taking the time to be a part of this session. So, without further delay, let's move on to the topic titled AM and FM receiver. Before moving ahead, here's a quick overview of today's lecture titled AM and FM receiver. Let us briefly discuss today's lecture flow. First, we will deal with the introduction to AM and FM receiver. Then, some historical developments of AM and FM receivers. We will discuss types of AM receiver. Then, we discuss the TRF receiver block diagram. We will discuss the super heterodyne receiver block diagram. We will also take into consideration an FM super heterodyne receiver. We will discuss about the various components and we will discuss in that the importance of AGC, automatic gain control in receiver. We will also have a look on the key differences between an AM and FM receiver, some interesting facts about AM and FM receiver, applications of AM and FM receivers, challenges and innovations in receiver design. And finally, we will have the conclusion part. So, let us first start with the introduction to AM and FM receiver. AM, amplitude modulation, and FM, frequency modulation receivers are fundamental component in communication system, crucial for receiving and demodulating radio signals. Each types of receiver is designed to decode specific modulation technique used in broadcasting and telecommunication. AM receiver operates by detecting variations in the amplitude of the received signal, translating this changes into sound waves or data. Historically, AM played a pivotal role in the early radio broadcasting, offering widespread coverage and simplicity in receiver design. It remained relevant today in applications such as broadcasting news, talk shows and music across long distances. FM receiver on the other hand utilize frequency modulations to encode the audio signals onto radio wave. This methods preserves the signal quality by minimizing amplitude variations, resulting in clear audio reproduction compared to AM. FM gain pioneers for its superiority sound fidelity, making it ideal for music broadcast and high quality audio transmission. Both AM and FM receivers are integral to modern communication system, serving diverse purpose for commercial radio broadcast to emergency communication channel. Their importance extends beyond entertainment, impacting public safety, information dissemination and global connectivity. Understanding the operation and significance of AM and FM receiver provides a foundation for comprehending how radio waves are utilized in everyday communication, makes them essential topic in the study of communication system and broadcast technology. Before moving ahead, let's discuss some interesting historical development of AM and FM receiver. The earlier development of AM receiver makes a significant milestone in the history of broadcasting. Amplitude modulation was among the first modulation technique used to transmit audio signals over radio wave. In early 20th century, pioneers like Edwin Armstrong made breakthrough in radio technologies, leading to the commercialization of AM broadcasting. The early AM receiver plays a crucial role in stabilizing radio as a mass communication medium, enabling widespread of news, entertainment and cultural program. FM, pioneered by Edwin Armstrong in 1930s, offered distinct advantages over AM by encoding audio signals onto radio waves through frequency variations rather than amplitude change. This innovation drastically reduces noise interferences, resulting in clear sound reproduction and high fidelity. FM receiver quickly gained popularity for their superior sound quality, making them a preferred choice for music broadcast, high fidelity audio transmission and specialized applications requiring clear and reliable reception. The development and standardization of FM broadcasting standards further solidified its position in radio industry, paving the way for stereo broadcast and expanded programming option. In summary, the historical development of AM and FM receivers reflects the evolutions of radio technologies from its early experimental stage to its widespread commercialization and modern application. These advancements not only revolutionized the broadcasting capabilities, but also underscored the importance of modulation technique in shaping the landscapes of communication system and media disseminations. Now, let us focus on the types of AM receivers. The two widely used AM receivers are tuned radio frequency, abbreviated as TRF receiver, and the super heterodyne receiver. So, let us first take the tuned radio frequency receiver. The tuned radio frequency receiver was one of the earliest types of AM radio receiver developed in the early 20th century. It consisting of multiple tuned radio frequency stages, each tuned to the frequency of the desired radio station. Here are the key characteristics and working of a TRF receiver. First, the designing and operation. The TRF receiver typically consists of several RF amplifier stages, each followed by a tuned circuit, which is basically a LC circuit that resonates at the frequency of the incoming radio signal. Each stage is tuned independently to the frequency of the specific radio station. The incoming radio frequency signal is amplified by each stage in succession, and with each stage helping to select and amplify the signal within the tuned frequency range. The advantages of using tuned receiver is it's simple in design and construction, provides a good sensitivity and selectivity when properly tuned. The disadvantages associated with it is susceptible to frequency drift and image interferences, limited selectivity and stability compared to super heterodyne receivers. The TRF receivers were widely used in the earlier days of radio broadcasting before the advent of super heterodyne receiver. They played a crucial role in popularizing the radio receptions in household and early broadcast station. Now, let us discuss the second types of the receiver, that is a super heterodyne receiver. So, a super heterodyne receiver revolutionized the radio technologies and become the standard design for most AM and then later on for FM also, due to its improved performance and stability. Here's how the super heterodyne receiver works and its key characteristics. First of all, let us deal with the design and the operation part. The super heterodyne receiver used a local oscillator to mix the RF signal with a fixed frequency signal produced by the local oscillator to produce an intermediate frequency abbreviated as IF. The IF signal is then filtered and amplified by subsequent stages of the receiver. The intermediate frequency is fixed and do not vary with the incoming signal frequency, allowing for a better selectivity and stability. The advantages are improved selectivity and stability compared to TRF receiver, reduce susceptibility to image interferences and frequency drift, allowing for easy tuning and better performance across a wide range of frequency. There are some disadvantages too: more complex circuitry and design compared to a TRF receiver, and initial cost and complexity may be higher. Invented in early 20th century by Edwin Armstrong, the super heterodyne receiver quickly becomes the standard design for AM and later FM receiver. Its introduction marks a significant advancement in radio technologies, allowing for a better reception quality and tuned accuracy. Both type of receiver has contributed to the evolution of radio broadcast and communication system, with the super heterodyne receiver offering superior performance and becoming the dominant design in modern radio receiver due to its improved selectivity, stability and ease of tuning. Now, let us have a detailed description of each of this receiver. First of all, the tuned radio frequency receiver. The first block is the RF amplifier. The RF radio frequency amplifier is the initial stage in a TRF receiver. Its primary function is to amplify weak radio frequency signals received by the antenna. Here's how it works. The RF amplifier boosts the amplitude of the incoming RF signal to a level sufficient for further processing. It operates at the frequency of the desired radio station and typically includes a tuned circuit, often an LC circuit, that resonates at this frequency to enhance selectivity. Provided initial amplifications to overcome the inherent noise and losses in the antenna and the transmission line, set the stage for subsequent stages to process the signal more effectively. Now, the designing consideration must be tuned to the frequency of the desired radio station to maximize signal reception. Selectivity is critical to reject unwanted signals and noise. The second component is the detector. The detector stage in the TRF receiver is crucial for extracting the audio signals from the modulated carrier wave. This stage follows the RF amplifier and precedes the audio amplifier. The function is convert the modulated RF signal which carries the audio information into baseband audio signal. Typically, it demodulates the amplitude modulated AM signal and recover the original audio frequency variations. There are different types of detectors that can be used. The first one is a diode detector, often used in the early TRF receivers, where a diode rectifies the RF signal to extract the audio component. Then an envelope detector, common in modern TRF design, which utilize components like capacitor and resistor to smooth and extract the audio signal. The output of this detector is produce a varying voltage or current that correspond to the audio signal imposed on the carrier wave. Next step is the audio amplifier. The audio amplifier stage in the TRF receivers amplifies the weak audio signal extracted by the detector to a level suitable for driving a speaker or headphone. The function is increase the amplitude of the audio signal to an audible level without introducing significant distortions, provide sufficient power to drive a speaker or headphone transducer. The characteristic is typically operates in the audio frequency range of 20 Hz to 20 kHz and has a linear response to faithfully reproduce the audio signal. May constitute of one or more stages of amplification to achieve the desired output level. Signal fidelity and low distortions are critical to ensure accurate reproductions of audio signal. Impedance matching with the output transducer, speaker or headphone is essential for effective power transfer. The next component is the power amplifier. In some TRF receiver design, especially those intended for driving speaker directly, a power amplifier stage may be included. The function is provide additional amplification to drive speaker or other high impedance load, increase the power level of the audio signal to a level sufficient to produce audible sound. The characteristic is operate at high power level compared to that of an audio amplifier, ensures that the audio signal can drive the speaker efficiently without distortion or loss of fidelity. Implementation may use transistors or vacuum tube valves depending on the design era and requirement, ensures that the audio signal remains clear and undistorted throughout the final stage of amplification. So, each blocks in TRF receiver plays a critical role in extracting the process and amplifying the audio signal from the received RF carrier wave, ultimately delivering clear and a good audio to the listener through speaker or headphone. Here is a detailed description of each blocks of super heterodyne receiver now. In super heterodyne receiver, the first stage is RF amplifier multi-stage. The RF radio frequency amplifier stage in super heterodyne receiver is designed to amplify the weak radio signals received by the antenna. In super heterodyne receiver, this stage often consists of multi amplification stages. The function is amplify the weak RF signal picked up by the antenna to a level suitable for further processing, enhance the signal strength to improve the signal to noise ratio and overall receiver sensitivity. The characteristics typically includes multiple stage of amplifier, often use transistor and vacuum tubes to achieve sufficient gain. Each step may be tuned to a specific frequency or band to maximize selectivity and reject unwanted signal. Now, the designing consideration required carefully designed to ensure stability, gain, linearity and minimal noise figure. Often employ tuned circuit such as LC circuit to select the desired frequency and reject others. The next component is the mixer stage. The mixer stage in super heterodyne receiver is crucial for frequency conversion, translating the received RF signal to a lower intermediate frequency signal. The function is combine the RF signal with a local oscillator signal to produce an intermediate frequency signal, generates sum and the different frequency with the difference frequency being the desired IF signal. The operation is the mixer stage typically use nonlinear components such as diode and transistor to achieve frequency mixing. It selects a specific frequency, then it easier to amplify and process that original RF frequency. Output, the output of IF signal which is easier to filter and amplify than the original RF signal. The next step is the IF amplifier. The IF intermediate frequency amplifier stage in a super heterodyne receiver amplifies the intermediate frequency signals generated by the mixer. The function is amplify the relatively weak IF signals to a level suitable for detection and further processing, provides additional gain to compensate for loss and subsequent stages and improve receiver sensitivity. The characteristics operate at the intermediate frequency determined by the mixer stage, typically includes multi-stage of amplification to achieve the required gain. Designing considerations must have high gain, low noise figure and good linearity to preserve signal integrity, often used to tune circuit to select the desired IF frequency and reject out of band signal. The next component is the detector. The detector stage in super heterodyne receiver extract the audio or the data signal from the IF carrier. The function is demodulates the IF signal to recover the original audio or the data modulated imposed on the RF carrier. Convert the IF signal into baseband audio or data signal suitable for further amplification and reproduction. Types of detector. There are some different types of detectors. One is the envelope detector, common in AM receiver, which rectifies and filter the IF stage to recover the audio signal. Discriminator, common in FM receiver, which detects the frequency variations in the IF stage to recover the audio signal. The output of this detector will be produce a varying voltage or current corresponding to the original audio or the data signal. Then the next component in the super heterodyne receiver will be the audio amplifier. The audio amplifier stage in super heterodyne receiver amplifies the audio signal extracted by the detector to a level suitable for driving speaker or headphone. The function is increase the amplitude of the audio signal to a level sufficient for audible sound reproduction, produce sufficient power to drive speaker or headphone with clarity and fidelity. The characteristic of this component is operates in the audio frequency range of 20 Hz to 20 kHz with a linear response to faithfully reproduce the audio signal, may consist of one or more stages of amplifications to achieve the desired output level. The designing considerations are must ensure low distortion and high fidelity to accurately reproduce the original audio signal. Impedance matching with the output transducer, speaker or headphone is crucial for efficient power transfer. The next component in super heterodyne receiver is the power amplifier. In some super heterodyne receiver design, especially those intended to drive speaker directly, a power amplifier stage must be included. The function is provide additional amplification to drive speaker or other higher end impedance load, increase the power level of the audio signal to a level sufficient for producing audible sound. The character stages operate at higher power level compared to that of the audio amplifier to drive speaker efficiently, ensures that the audio signal remain clear, undistorted throughout the final stage of amplification. The implementation is may use transistor integrated circuit or vacuum tubes valves depending on the designing era and power requirement, ensures that the audio output is sufficient for the intended applications, ensure that the audio output is sufficient for the intended application, whether it is broadcast, communication or entertainment. So, each block in super heterodyne receiver contributes to the overall process of receiving, processing and amplifying radio signals to deliver clear and good audio or data to the listener or the user. Now, we will extend our discussion on super heterodyne receiver a little further. Previously, we have discussed an AM super heterodyne receiver. A slight modification in the AM super heterodyne receiver makes it a FM super heterodyne receiver. Okay. So, here is the block diagram of the FM super heterodyne receiver. Most of the blocks are common in FM super heterodyne receiver as compared to an AM super heterodyne receiver. The RF stage is common, the mixer stage is common, the IF stage is common and the audio amplifier stages are common. But in addition to that, we have the limiters, discriminators and de-emphasis. De-emphasis we already discussed in great detail. Let us have a look on this super heterodyne FM receiver. The signal received by the antenna is amplified by the RF amplifier. The amplified signal is then applied to the mixer, which is the signal received by antenna is amplified using RF amplifier. The amplified signal is then applied to mixer, in which the second signals come from a local oscillator. The mixer now have two input frequencies, combining both generates an IF signal of 10.7 megahertz. The signal is again amplified using an IF amplifier. The output of the IF amplifier is allowed to flow in the limiter circuit. Now, the limiter circuit gives a constant amplitude signal by removing the noise from the signal it received. The output of the limiter is then applied to FM discriminator, which recovers the modulating signal. This signal is still not the original modulating signal. Therefore, before applying it to the audio amplifier, it is de-emphasized. So, de-emphasize attenuates the higher frequency component to bring them back to their original amplitude. The output of the de-emphasis is the audio signal, which is applied to the audio stage and then to the speaker. Now, let us discuss an important component, that is automatic gain control, abbreviated as AGC, in super heterodyne receiver is a crucial mechanism designed to stabilize the receiver's output signal level despite variations in the received signal strength. Here is a brief explanation of it. Mainly, the purpose of AGC is to maintain a relatively constant output level from the received audio or IF stage, regardless of the change in the strength of the incoming RF signal. The operation is AGC circuit continuously monitor the strength of the received signal, typically after the mixer stage. Based on the detected signal strength, AGC adjusts the gain of IF and audio amplifier stage. It operates in feedback loop, where changes in the signal strength leads to corresponding adjustment in the gain, ensuring that the output signal levels remain within the specified range. Now, by stabilizing the output signal level, AGC prevent distortion and ensure consistent audio and data quality. It helps in minimizing noise and interferences by reducing the strong signal condition and increasing it during the weak signal condition. AGC extends the receiver dynamic range, allowing it to handle a wide range of signal strength without a manual adjustment. Implementation. AGC is typically implemented using feedback control circuit that adjusts the bias or gain of the amplifier in response to the input signal strength. This is all about the different types of receivers. Now, let us have a comparison between an AM and a FM receivers. The first comparison is based on the modulation technique. The AM and the FM are two primary modulation techniques used in the radio communication system. AM works by varying the amplitude of the carrier signal in proportional to the audio signal amplitude variation. The FM varies the frequency of the carrier signal in response to the audio signal amplitude variation. In receiver design consideration, AM receiver are designed to demodulate amplitude modulated signal, detecting the variations in signal strength caused by the audio modulation. FM receiver on the other hand are more complex in design compared to that of the AM receiver. They must accurately demodulate frequency modulated signal by detecting the change in the carrier signal. The FM includes components such as frequency discriminator, detector circuit to recover the original signal. In summary, the key differences between AM and FM receiver lies in their modulation technique and designing considerations. Some applications of AM and FM receivers. It is used in broadcasting, emergency communications and entertainment. In conclusion, AM and FM receivers continues to play a pivotal role in broadcasting, emergency communications and entertainment industry worldwide. So, with this we have come to an end of today's lecture. Thank you for your attention. Before we conclude, I want to take a moment to thank all of you for your participation, attention throughout this lecture. Take care. Have a great day. Thank you all.